All right. So a couple more things in this section, and I don't even know what section we're in. Section 3, perfect. So I'm going to talk about signs on fractions. Okay? Because sometimes you can have a fraction that has a negative in front of it. And the whole idea of where does a negative go, honestly, doesn't matter. For example, right here, this fraction is saying -1/3. Okay? Now, to the right, I'm going to write this. This says 1 divided by, or 1 over -3. And then the last one is if that negative symbol is like right in the middle. It's right on the same level as the fraction bar. Well, they are all the same exact thing. So no matter what, no matter where that negative occurs, okay, no matter where that negative occurs, if there's one negative, the entire fraction is going to be negative. 99 times out of 100, I'm writing that. I'm putting the negative out front. Okay? All right? Like as my final answer, I'm just going to put it out front. So, the negative doesn't matter where it occurs. All right? The only thing you got to be careful about is if you run into this situation here. So if you have a double negative, a negative in a numerator, negative in a denominator, you got to remember that a fraction bar, it means division. It does. So you're dividing two numbers here with negative signs. And when you have two numbers that are both negative and you're dividing, it turns into what type of a number? Positive. Very good. So just make sure that when you come across this situation, you just take that extra step and rewrite it as a positive number. Okay? Are there any questions with that? All right, so let's look at the last. Last example here. Okay, so in this example, we just want to simplify. That's it. And this is going to kick in our order of operations. Remember them? I mean, just because we have fractions, the order of operations are still the same. There's nothing different. Okay? It's just now this looks much more complicated because you have this from a 30,000 foot view, you have just a big fraction. I dropped my pen. So you got this big fraction here, but that's not going to hurt us at all. It's not that hard. What we're going to do is this. We're going to simplify the top, simplify the bottom, and then at the very end is when we divide our numbers. So for this problem right here, let's focus on the numerator. We have 8 minus 4, or sorry, I read that incorrectly. We have the quantity of 8 minus 4 to the second power. So we're going to do the work inside the parentheses first. So we get 4 to the second power. And then 4 to the second power is going to be 16. Okay? Now let's worry about the denominator. Well, you don't have parentheses in a denominator, but you do have exponents. 8 to the second is 64. 4 to the second is 16. Okay, now 64 minus 16 is going to be 48. How are we looking so far, everyone? Pretty good? Okay, now from here, there is the question you need to ask yourself. Is this simplified? And to be honest with you, the only way you're going to know is by breaking these numbers down. Okay? So real quick, 16 is 4 times 4. And each 4 breaks down into 2 times 2. The 48. Two numbers that multiply to get 48. How about 4 and 12? The 4 breaks down into 2 and 2. The 12 breaks down into 2 and 6. And then the 6 breaks down into 2 times 3. You leaving? Have a good day. I love you. Yeah. So now let's write out the entire denominator. 2, 2, 2, 2, and a 3. Does everybody agree with that? I know this is exciting stuff, isn't it? Especially on a Monday. Now we reduce. Look for things that are the same in the top and bottom. Take your time. Don't rush. In the numerator, here's my first set of 2's. Then my second set of 2's. My third set. My fourth set. And since I scratched everything out in the numerator, I'm just going to write a number 1. Because remember, 2 over 2 is 1. So, is there anything else I can reduce? Nope. So your answer is 1/3. How are we looking? Pretty easy stuff. All right. Like I said, fractions, not hard. They're very tedious. It's like that one project that you just hate doing because it's tedious. It's not difficult. It's just tedious. All right, let's try this one. Now, this type of problem right here, it does have a special name. It's called a complex fraction because there's a fraction in the numerator and a fraction in the denominator of this big fraction. I don't care about that. I care that it's a complex fraction. But here's what I know. I know since I have this little fraction in a numerator and then a mixed fraction in a denominator, I'm dividing. So I can rewrite this problem as 7 over 9 divided by -2 and 4/5. And I know since I'm dividing these two, I need improper fractions so that -2 and 4/5 is going to convert. Give me a sec. Let me write this out. Now remember, that negative is out front. So put it out front. Okay? So 2 times 4 is 8. And 8 plus 5 is what, 13? So this is going to be -13 over 5. Does that make sense, everyone? Okay? So let's rewrite the problem nice and neat now. 7 over 9 divided by -13 over 5. Yes, Stevie?
You did that wrong.
I did?
Yeah, because isn't it 2 times 5 plus 4?
I did do that wrong. I got the numbers backwards.
Okay.
Stevie, can I use the excuse it's Monday?
Yeah.
Okay, thank you.
Uh-huh.
Stevie gets a gold star today. You remember gold stars when you were kids?
Yeah.
I got a funny story about a gold star. I'll tell you after this problem. So I just made the mistake. I transposed the numbers, but I fixed it. Actually, I didn't fix it. Stevie fixed it, so thank you. So now we have 7 over 9 divided by -14 over 5. Crystal, did I lose you?
I was looking at the same thing Stevie was looking at. I was like, wait, what?
Hey, yeah, I'm not
That's
perfect.
what I was no, that's what I was looking like. What?
No, I'm not perfect. Exactly what Stevie just did. If you think I made a mistake, unmute and just say, wait a minute. I think you made a mistake. I'm not going to take offense to it. I'm not perfect. So, now, let's rewrite the first fraction. Division changes the multiplication. And I will flip the second fraction. So now from here, it's just a matter of me simplifying before I multiply. 7's prime, it stays the same. 9, 3 times 3. Times a negative. 5 is prime, it stays the same. 14 is just 2 times 7. Now, I need you to kind of realize my technique didn't change even though there's this negative right here. Like nothing changed. I just kept doing what I'm used to doing. Okay? So now I'm going to write one big numerator and one big denominator. And I'm going to put the negative all the way out front. So there's my numerator in order. My denominator is right there. And my last step here is just to simplify if I can. So I'm just going to scratch out the 7's. And write my final answer as negative 5 over, what is that? 2 times 3 is 6. 6 times 3, 18. So my answer is negative 5 over 18. How are we looking? Pretty good? All right. So,
can you do one more example?
Sure. Just like this or like this one or like
yeah, like the one you just did.
Okay. So let's see here. Let me find another one for us. Let's see. We'll try. No, I'm not going to try. You're going to try this one. There you go. Anybody get an answer yet, or are we still working? All right. Anybody get an answer yet?
Negative 1 over 18.
Negative 1 over 18. Anybody else get the same thing or something different? All right, let's go over it. First, we have a fraction divided by another fraction. So let's just rewrite it in a normal way, something we're used to seeing. Okay? Let me write this off to the right here. There we go. Now I can see this second fraction is a mixed number, so I need to convert that. So it's going to be 6 times 4 plus 3 over 4. Did I set that up correctly this time? All right, good. 6 times 4 is 24 plus 3 more. It's going to be 27 over 4. So I have 3 over 8 divided by a negative 27 over 4. So rewrite the first fraction. Reciprocate the second, which means to flip it. Oh, sorry. That changes to multiplication. So now, I simplify first, multiply second. The 3 prime stays the same. 8 is going to be 2 times 4. Times the negative symbol, second fraction. 4, I'm going to leave that the same. The reason why is because in the first fraction, I already have a 4. 27 is going to be 3 times 9. Do we all agree with this so far? Now, maybe you broke it down even further. Maybe you wrote this, and I'm going to write it in red, and it's still going to be the same thing. Okay, maybe you broke that down even further, and that's fine. Doesn't matter. What we're going to do is we're going to write one big numerator and one big denominator in order. And I'm going to be using the black writing. So we're going to have a negative out front, 3 times 4 in the numerator. And then in my denominator, I'm going to have a 2 times 3 times 4 times 9. Now I'm looking for numbers that are the same on the top and bottom. That's going to be the 3, and that's going to be the 4. Since everything is scratched out in the numerator, I put a 1. So I get a negative out front, a 1 in the numerator. And then in my denominator, 2 times 9 is going to be 18. So it's negative 1 over 18. In red, if you decided to break everything down, watch what happens. You have a negative out front. That 3 and that 3 reduce. This 2 and this 2 reduce. That 2 and that 2 reduce. Since everything's scratched out in the numerator, you put a 1. 2 times 3 is 6. 6 times 3 is 18. You still get the same answer. It's just how far did you break it down? That's it. Are there any other questions? All right. So let's move on to the next section, which we need to go back in time. We're going to go back to that chapter 2. I think it's section 4. Let me look here. Nope, section 5. My bad. And let's go ahead and let's clean up our mistakes here so it looks all nice and neat. Section. And I'll put a P there. All right. Now, before we get started with this, I'll tell you the good story. Because maybe you could do this to your, I don't know, family members, significant others, kids, whatever. I was watching this this TikTok. I told you the first day of class, I'm like addicted to TikTok. It's really easy to watch when I'm taking the dog out. And this, I don't know, I guess it was the guy's wife. She had this, like a chores list. And she would put like stars. Or no, it wasn't even a list. She had like his name with like gold stars. And every day he got like another gold star. And he never understood why. So every day he would come down the steps and he would look at the chart and it's like, oh, I must have did something good yesterday. I got another gold star. Start feeling good about himself. Well, one day she didn't put a gold star out. And like all day he was like, what didn't I do? Like he was driven by the gold star. So try that with your family. See if like one of the kids or something like that goes, how come I didn't get a gold star today? Just see what happens. I think that would be kind of funny. No? Am I on an island by myself here? I guess I'm on an island by myself. All right. Anyways, since nobody laughed, we're going to go back to chapter 2 now. So chapter 2, we learned prime factorization in section 5. All right? We're going to take that and we're going to extend it a little bit because here's what we're going to be learning. Let me get out a black marker here. You don't have to write this down because I'm not doing the problem. I'm just going to show you this is what we're going to get to. 1/5 plus 2/10. Adding and subtracting fractions, completely different from multiplying or dividing. Multiplying and dividing is very easy. It's just simplifying and then writing your answer. Adding or subtracting, you can't add these two together. They're different. All right? So you got to find what we call a lowest common denominator. And there are tons of ways that we could do this. Maybe some of you in the room right now can already see what the denominator would be. Maybe some of us can't. My goal is to make this as painless as possible. So in order to do this, we're going to learn how to find an LCM, which stands for lowest common multiple. Now, the idea behind a lowest common multiple would be something like this. Find the LCM for 2 and 3. So what you would do here is you would go ahead and start writing out the multiples of 2. Because if you think about it, it's the lowest common multiple. Multiples are, for 2 would be 2, 4, 6, 8, 10, 12, and so forth. Because 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. So 1, 2 times 1, 2 times 2, 2 times 3. Like, that's how I'm getting those numbers. Now, I'm going to write it for 3. So 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 15, or I'm sorry. 3 times 4 is 12. 3 times 5 is 15. 3 times 6 is 18, and so forth. Now, when we talk about the lowest common multiple, we're looking for the smallest number that both of these rosters have in common. And that would be the 6. So in this situation, the LCM for 2, 3 is going to equal 6. Okay? Now, here's what's nice, Kim. These numbers are small, 2 and 3. What happens when the numbers get large? Do you really want to be writing out these multiples in this big roster and then trying to find the smallest one? I agree with you. I want to work smarter, not harder. All right? So there is another way that we approach this, and it's called the prime factorization method. Here's how we do it, okay? And it's nice. There are steps. And if you could bake a cake for a birthday party, you could do math. So, step 1. You're going to find the prime factorization for each number. All right, step 2. You're going to label the LCM as follows. So your LCM is going to equal the product of unique primes. Now, in order for us to understand this, I need to ask these questions. First, what does product mean?
Multiplication.
Good. Unique primes. What's that mean?
Like numbers that are reduced as much as
Not reduced.
um
Not reduced. Think about it. I'm gonna get my dog. Come on, buddy. Come on. You coming inside? No? Okay. Not reduced. What's unique mean?
It's a certain kind of number.
Okay, well, they are prime numbers. Stevie, can I ask you a question?
One of a kind.
Ah, I don't have to ask you anymore. Ashley's correct. Unique is one of a kind. I was going to ask Stevie, how many children do you have? And I think you have what, 3? 4?
Yeah.
2? And are they the same or are they different?
They're different.
They're unique. So when we say the product of unique primes, we're looking at the multiplication of different prime numbers. Now, there is the last step. You got to find the exponent for each unique prime. And to do this, to find this, you're gonna look at each prime number and you're gonna look at the factorization. And whichever factorization has the most, that's gonna be your exponent. All right? So go ahead and write that down, and then I'm gonna show you how this works. It's very easy. Okay, we good? All right. So here we go. We're going to find the LCM for 15 and 18. So step 1. Let's find the prime factorizations. 15 equals 3 times 5. 18 is going to equal, well, 18 I actually got to break down a little bit. So 18 is 2 times 9. And then 9 is 3 times 3. So I get 2 times 3 times 3. Are we all on the same page so far in terms of prime factorization? All right. Now, step 2. We're at the LCM. And now we're going to write the multiplication of unique primes. How many different unique primes do we see here? How many different unique primes do we see?
3,
3 of them. What are they, Stevie?
2, 3, and 5.
2, 3, and 5. I agree. So now this third step is going to be finding the exponents on these. So let's start with the number 2. I'm going to look at every single prime factorization, and whichever one has the most 2's, that's the one I use. So this is, honestly, it's like kind of like a yes or no question. In the number 15, do you see any number 2's? Yes or no? I agree, no. What about in number 18? Do you see any 2's? Yes or no? How many? 1. So the exponent's going to be a 1. Good? Now we move on to the number 3. In 15, do we see any 3's? Yes or no? Yes, only one of them. What about in the number 18? How many? 2. So the exponent's going to be a 2 because in 18, it has the most 3's. Does that make sense, everyone? Now, what about the number 5? Well, the 15 has a 5. The 18 does not. So this is going to be 5 to the first. So your LCM is going to be, and I'm going to write this out now, 2 times 3 times 3 times 5. 2 times 3 is 6. 6 times 3 is 18. And 18 times 5 is 90. And that is your LCM right there. Does that make sense, everyone? See, if we did the traditional roster method like I did at the very start of the class, you would have to write all the multiples of 15 and 18, and then you'd have to find the number 90. That would be the lowest common multiple. So you could do it that way, or you could do it the prime factorization method. I really like this method because we're already used to doing prime factorizations. Are we all on the same page so far? All right, let me give you one to do then, okay? Let's change the numbers up a little bit. How about find a prime factorization of 12 and 36? Coming in? Coming in? Okay. Anybody get an answer yet?
Got 432.
432.
Yeah.
Okay.
I did something wrong.
Yeah, I think you did something wrong.
I got 36.
Yeah, the answer, I think the answer is 36. So let's walk through it together. Let's make sure. Step 1, prime factorize. 12 is going to be 2 times 2 times 3. 36 is going to be 2 times 2 times 3 times 3. Now, if you're asking, well, how did he get that? What I did is I just broke this down. All right, so 12 is going to be 2 times 2 times 3. And then 36, well, that's going to be 6 times 6. And then 2 times 3 for each of them. Good? All right. Just going to erase it.
Did I mess up because I did 3 times 4 for 12?
No, that still works. Here. Ready? Here's 12. 3 times 4. Now you got to break down the 4 into 2 times 2. But,
I didn't do that. That's
oh, okay. Yeah. You got to break it down. Now, step 2, we're going to write LCM equals the product of unique primes. Well, I only see 2 of them. 2 times 3. Those are the different ones. Now, let's look at exponents. So in the 12, how many 2's do you see? 2 of them. In the 36, how many 2's do you see? 2 of them. So the exponent is going to be what? A 2. Very good. Now the 3's. In the number 12, there's 1. However, in the number 36, there's 2 of them. So the exponent is going to be a 2. Because you're looking for the most in any one prime factorization. Does that make sense? I think that's the hardest part. You're looking for the most in any one prime factorization. So now we can go ahead and simplify this. The LCM is going to equal, well, 2 to the second is 4. 3 to the second is 9. And 4 times 9 is 36. Does that make sense, everyone?
Wait, hold on. How did you get 2 to the second power?
How many?
Wouldn't it be 2 to the fourth power?
No. Listen to what I'm saying. It's the most in any one prime factorization. So you have 2 of them here and you have 2 of them here. So it's just 2 to the second because it's any one prime factorization, not both, any one. Here, maybe look at it like this. You ready? This method, it's just called. I don't even know if it has a name. Just Kim, are you watching? Your LCM is going to be this. You just draw arrows straight down. Does that make sense? If I like do it that way. Now, the only problem with this method that I just used, okay, is you got to make sure you write very neatly. All right? Because you got to space everything out. Like, everything has to be evenly spaced. Why don't we do another one? We're going to do another one. So we're going to find the lowest common multiple for 60 and 72. Step 1, break it down. Prime factorization. 60 is going to be 10 times 6, 2 times 5, 2 times 3. And I'll put them in order. 2 times 2 times 3 times 5. 72 is 8 times 9. The 8 is going to be 2 times 4. And the 4 is 2 times 2. And the 9 is going to be 3 times 3. So 72 equals. Now, I'm going to write them in order. 1, 2, 3 2's. And then 2 3's. Okay? How are we looking so far, everyone? All right, now I'm going to do that arrow method thing again. All right, I'm going to do the arrow method thing. But what you got to do here is you got to leave yourself space. Okay, come on. No, not right now. Not right now. All right, does everybody see how I left myself some space? Okay. So my LCM is going to be, you drop down, you always just draw an arrow straight down. 2, 2, 2, times 3, times 3, times 5. Okay? So this is going to be, let me zoom out here a little bit. The LCM is going to be 2 to the third times 3 to the second times 5. You'd have to multiply all that out. So let me do that real quick. I got my calculator right here. Save us some time. 2 to the third times 3 to the second times 5. So it's going to be 360. Now, you see the exponents, 2 to the third, 3 to the second times 5. Everybody see that? Here's what I'm saying, Kim. If we came all the way back up into here, the product of unique primes is 2 times 3 times 5. Now, I'm looking for just the most number of 2's in any one prime factorization. So in a number 60, there are 2 2's. But in a number 72, there's 3 of them. So I know that exponent is going to be a 3. Now, for the number 3, well, in the number 60, there's only 1 3. But in the number 72, there's 2 3's. So I know that's going to be a 2. And then for the number 5, the number 60 has 1. The number 72 doesn't have any. So I know that's going to be to the first. So I get the same exact thing. Now, the arrow method is really nice because visually you get to see it, and that's fine. I don't care if you want to do that. But you got to rewrite it so it's all spaced out. Otherwise, you can't draw the arrows. Like all your 2's have to be grouped, all your 3's, all your 5's. My method just kind of takes that out of the equation. You do either. You do either. Okay? I just need to know, do we all understand how I got what I came up with, regardless of the method? Okay? How are we looking so far, everyone? All right. Let's do one more of these problems. Okay? Except this time, I'm going to give us a little bit more. Find the lowest common multiple for 8, 12, and 20. I don't care how you do it. Just do it. Okay, we ready? Who got an answer? What was it? The LCM equals what?
120.
I agree. LCM is 120. Now, let's break it down. Step 1, prime factorize everything. 8 is going to be 2 times 2 times 2. I'll write it underneath here. 12, we do 12 a lot, so hopefully we have that one kind of memorized. 2 times 2 times 3. 20 is 4 times 5. And we could break that down into 2 times 2. So 20 equals 2 times 2 times 5. So now I'm just going to stack them on top of each other. We'll do both methods here. So this will be floaters, and this will be the arrow. So 8 equals 2 times 2 times 2. 12 equals 2 times 2 times 3. And 20 equals 2 times 2 times 5. So do my method first. So I know my LCM is going to be 2 times 3 times 5. I need to worry about exponents. So the number 2, well, in this prime factorization, there's 3 of them. And this one, there's 2 of them. And here it's 2 of them. So it's going to be 2 to the 3rd. Do we all agree? Okay. Now I need to worry about the number 3. There's 0 number 3s. There's 1. And there's 0. So that's going to be a 1. And then the number 5. There's 0 in the first, 0 in the second, 1 in the fifth. Or, sorry, 1 in the third. So I get 2 to the 3rd times 3 times 5. Are we all on the same page there? All right, so we're looking pretty good, right? All right. So 2 to the 3rd is what? 8. 8 times 3 is what? 24. And 24 times 5 is 120. Good? Yes or no? All right. Now, here's the arrow method. Arrow method, you got it. You got to space it out. So 8, 2 times 2 times 2, 12, 2 times 2 times 3, and then 20, 2 times 2 times 5. So you put the 5 all the way on the end. Now the LCM, draw arrows straight down. A 2, a 2, and a 2, a 3, and a 5. But if you notice, you still get 2 to the 3rd times 3 to the 1st times 5 to the 1st, which is still going to be 120. Good? Any questions? All right, because we're going to use this technique to help us build what we call equivalent fractions. And that's how we add fractions. Denominators got to be the same. But we'll worry about that in the next class.